All right, so we are getting started. Again, please make yourself muted if you have joined on the Zoom link. I'll go through the problems on the board because right now the screen is not working. Okay, so last year we started discussing about electronic circuit analysis, and as you know that you have already learned about some of these analysis methods, including nodal analysis, loop analysis, etc. in your previous class. In this lecture, however, we follow one particular method because you already know these methods of analyzing the circuits. So what we are going to do today is kind of look at what are the techniques. For example, if you look at a circuit, how should you go about analyzing it using the multiple techniques that you have already known. And in the method, we'll try to also make sure that all of us can eventually reach to the same goal, that is analyzing the circuit correctly. Whatever method you apply, that does not matter in the long run. But the important thing is that you have to learn analyzing the circuits in a correct way and in a fast way. So for example, when you go for interviews in TI or analog devices, what they look for is that whether you can analyze the circuit fast. Of course, you have to do it correctly as well, but building that fastness or building that speed when you are trying to analyze the circuits, that's very important. So please make sure as you look through the different problems, there are more problems that have been uploaded on Canvas. Try to make sure that you understand how to analyze the circuit and how to analyze the circuit fast. We'll see a few examples today, but again, please make sure that you practice as many as you can. All right. So in the last lecture, we have looked into, I think a few of you haven't played your users, so please mute your device because there will be a lot of echo. All right, perfect. Thank you. So last lecture, we have looked into some of these very few basics, like what is Ohm's law, what is KCL, what is KVL, and how do you use KCL and KVL to analyze certain circuits. Also, we'll be looking at voltage or current sources. On this slide, you are seeing ideal voltage sources, ideal current sources, which are dependent as well as independent. So if you're looking at a dependent voltage source, it may look something like this. If this is a DC voltage source, that's how an independent voltage source will look like. If it is a dependent voltage source, generally the symbol looks like this. Similarly, if you're looking at a current source, it may look like this if it is independent, and if it is dependent, generally you represent it like this. And what does independent current sources mean? That if the value of the voltage is not dependent on anything else in the circuit, then that is a dependent voltage source on an independent current. If the value of the voltage source depends on anything on the circuit, right? Let's say any other source, a particular resistance, any other particular component on the circuit, that becomes a dependent current source for a dependent voltage. We have also looked into voltage and current in the last lecture. But as you know that you have these series resistances RA and RB, equivalent resistance in series becomes RA plus RB. On the other hand, if you have parallel resistances RA and RB, the parallel combination of them then becomes. So let me just draw it on the board as well so that you can visualize. So this is RA and this is RB. Then the series combination is going to be RA plus RB. On the other hand, if they are parallel, this is your RA and this is your RB. Then the parallel combination looks like this equation: RA times RB divided by RA plus RB. And this is something we have proved in the previous lecture already. So students who came in late for them, so students system is malfunctioning. So we are looking at our mobile device on the Zoom screen, and I'll be on the problems of the problem. All right. So in terms of current distribution and current distribution, we have looked into both. You know that when we are looking at steady resistances, the voltage develops across each of those resistances. So let's say you want to know what is the voltage developed across the RA resistance. If this is the voltage you want to find out, then that voltage developed across the resistance RA will be proportional to the value of the resistance RA. On the other hand, if you want to find out the voltage developed across RB, that will be proportional to the value RB. On the other hand, when you have parallel resistance, the current, so let's say this is your circuit, you have a voltage source over here, and then there is a current source here. So what that current does is that the current gets divided into two parts, one flows through here, one flows through here. And the amount of current that flows through each of these resistors depend on or is directly proportional to the value of the other resistor. And that is because resistance, the job of a resistance is to resist the current, right? So it means that if your value of resistance is higher, the current flow will be lower. And if the value of resistance is lower, the current flow will be higher. And that is why the current flow through one of these resistors will be dependent on the value of the other resistor. That's what we learned in the last lecture. Again, some of the students join yourself because otherwise there will be a echo in the recording. All right. Something that we want to learn is about amplifiers. So what does amplifier mean? And whether we get talking about amplification, are we talking about DC amplification or AC amplification? That is a very important concept to learn and remember. So the basic symbol for an amplifier is this. You provide an input voltage at the input side, and you have an output voltage. And this is the gain of the amplifier. As you kind of guess from the name, the amplifier is supposed to amplify voltages. Now, does it amplify DC voltages? If you provide a 1 volt DC and if the gain is equal to 5, does it give you a 5 volt DC at the output? The answer is no. The amplifier job is not to amplify DC voltages. An amplifier can never amplify DC voltage. So if you have a DC battery at the input, you never see a DC amplified voltage at the output. That cannot happen. Why that cannot happen? Of course, there are other circuits that can do that to some extent. For example, those will be called, sometimes you may have heard about DC to DC converter. So if you have a DC at the input, you want a DC at the output, you might want to use a DC to DC converter. But the amplifier's job is to amplify an input AC voltage or an input AC current to an output AC quantity. What does AC mean? You know, AC is about alternating current or alternating voltage. So let's say you have a sine wave at the input, and the output you can expect to have an amplified value of the sine. The job of an amplifier is to amplify AC voltages or currents. It can never amplify DC voltages or currents. That's a very important concept to remember. Now, you may ask that whether am I violating conservation of energy? Right? Because you know that if you cannot create energy, you cannot destroy it. Right? So how do you amplify a small signal or a small amount of energy, and you can call this a large amount of energy, right? So how do you do that? So for that, actually, if you just have an amplifier and connect an AC source to the amplifier, again, it does not work. You have to connect the amplifier to a supply. So let's say you connect the amplifier to a VCC, and you connect it to a ground. What that does, and we'll look into these concepts later. There is a concept called biasing. We'll be looking into a lot of biasing and what does biasing mean. Why it is important, we are going to look at that in our next few lectures. But for now, remember this, that whenever you have an amplifier and you want it to amplify a small AC signal, unless you connect it to the supply or unless you connect it to the ground, you cannot do that. And some of you already know this from your lab experiment. Yes.
What happens if you have like a DC offset in your AC signal before you feed it into the amplifier to get rid of that DC offset, or is it still coming?
That's a great question. So we'll be looking into those. So it depends whether it's a different amplifier or a single-ended mode, and that's a short answer. It might not be, or I might not be able to explain it right now without some of those discussions on what is a single-ended and what is a differential amplifier. But it is possible to amplify a small DC offset. Sometimes that happens, and sometimes you can design your circuit in a way that that small DC offset is gotten rid of. Ideally, you would want that small DC offset, and you don't want it. You want it to go away, right? And we'll see how it can be. But if you have this input small AC sinusoidal signal, and then the output, if you want a larger sinusoidal signal, what you do is that you connect your amplifier to a supply and a ground. There is always a current flow between the supply and the ground, as you know, and that supplies some additional amount of energy. So you're not actually violating the energy conservation law. You have a small amount of sinusoidal wave or a small signal sinusoidal wave, and the output you might have a larger signal or a larger amplitude. But you're not violating the energy conservation law because you have additional energy coming in from the supply. And that energy is used to amplify the small AC signal at the input to the larger AC signal at the output. And how you're going to utilize that energy coming in from the supply, that method is called biasing. It does not always, if you just connect it to supply and ground, it may or may not work correctly. There is also another additional concept of biasing, which we'll learn in this particular course. But this is how it works, that the energy from the input, the energy coming in from the supply, that gets combined in a beautiful way in the amplifier and eventually gives you a larger signal. So whenever we are talking about amplification, we are always talking about AC amplification. There is no concept of DC amplification in this course. However, in power electronics, you may learn about something called a DC to DC converter that can actually convert a 1 volt at the input to a 3 volt at the output, for example, or a 5 volt at the output. But the method of converting a DC signal to another DC signal is very different from what we'll be learning in this course for amplifiers. All right. One other important concept that I want to talk about in today's lecture is what if you cascade multiple amplifiers together? So let's say you have one amplifier with a gain of 5, and then put another amplifier with a gain of 5 after that. Right? What would be the overall gain? And by gain, what we mean is that what is your output voltage amplitude divided by the input voltage amplitude. So you know if this is a sine wave, the amplitude of the sine wave and amplitude can be defined in different ways. So for example, this is a peak to peak amplitude. That's what is the amplitude between the peak and the drop. You may also want to consider, let's say, half of that. So for example, this is A over 2, or let's call it K over 2. And if this total amplitude is K. So if your peak to peak amplitude is K, half of that is basically your common mode level or the DC level to the peak of the sine wave. And that's just called just the amplitude. And that will be called the peak to peak amplitude. That's the difference between these. Now, that's basically, that will give you your ratio of the output amplitude to the input amplitude, and that will be called the gain of the amplifier. So a gain of the amplifier of 5, if I say that will mean that if there is a AC quantity with a peak to peak amplitude of, let's say, 100 millivolt at the input, you'll see an AC quantity at the output with a peak to peak of 500 millivolt. If you cascade another amplifier after this, you would expect, maybe let me go to the other board, so you'll expect another sine wave, which is 5 times of 500 millivolts. So that would be 2.5. So this is called cascading of amplifiers, and you can cascade as many as you can, ideally, so that you can increase the amplitude from 100 millivolt to 500 to 2.5 volt and so on. However, there is a catch, there is a caveat. Whenever we talk about these amplifiers gain, we assume, and there would be a concept, as we learned, that there would be a concept of linear gain. If the amplifier is not in the linear region, if it becomes non-linear, you may or may not see this gain of 5. What does linearity mean? That if your input is a sine wave, your output should also look like a sine wave. That means that there is a 1:1 correspondence. The voltage at this point multiplied by 5 becomes the value of voltage at this point. The voltage at this point multiplied by 5 becomes the voltage at this point, and so on. Okay? So your output is directly A multiplied with the input. And that's a linear equation, because if you plot this, so if this is your input, if this is your output, the slope of this curve will be equal to A, that's the gain, which is output divided by input, and it will go through the origin. Also, it will be a linear curve. So that's why it's called a linear gain of the amplifier. However, there are possibilities, and you know that circuits are all about non-linearities and non-idealities. You will see that in certain conditions, your gain will not be a linear gain and your output may not be gain times it. And in that case, what it might look like is something like this. And this is very real in all amplifiers. Every amplifier that you encounter in life, it may look something like this. There would be a linear range, and then there would be a range when your output saturates. As you keep on increasing your input, your output will not increase anymore. Your output will saturate, and that region will be called the region of nonlinear. And how would the signals or the actual sine look like in that case? You might see that your sine is getting flipped at the top and the bottom. Yes, question.
Yeah, so when it's like becoming non-linear, like what is that? Like I see it's getting flipped, but what is like I guess like
the component should be fine, and I'll tell you why the component should be fine. Why I'm saying that it is becoming non-linear is because you will not see this spin gain of A. The gain will become something less than A. Then it will become something even lower. And eventually the gain might even become zero when this curve flattens out. Because the slope of this curve, when it is flat, it is zero, right? And the gain is basically the slope of this curve, the output input. If you plot that, the slope of that curve will be your gain A. Now, why would you see a flipping? There could be two reasons behind that. One, again, you can go back to your supply and the ground, the value of the supply and ground. What I said earlier is that if your input is 100 millivolt, you have a gain of 5, you get 500 millivolt. Again, you have a gain of 5, you have 2.5. But let's say your supply is only 2 volts. If your supply is 2 volts, you can never generate anything which is more than your supply. The supply is supposed to be the highest voltage in the circuit. And nothing can go beyond that. And that is the reason why the voltage will be flipped. And that flipped voltage will be the value of the supply or whatever. And on the bottom side as well, the value of the ground, which could be a 0 volt or let's say minus 2 volt, that is where it is going to get flipped on the bottom. Yes.
Why does it flip the signal instead of make the signal go back to 0?
That's a good question. So remember this, that when the gain is saturated, this is where the gain is saturated. The gain is not becoming 0. The gain is becoming a constant, right? Or basically, it is reducing, but it is not 0. Of course, if you go to infinite inputs, then you can call that, okay, my output to input ratio is almost close to 0. But the output voltage, as you see that the output is saturating. The output is not becoming 0. And what is the meaning of output saturating? Is that the output is getting flipped and it's not increasing anymore. Right? If it had increased infinitely, then you would see that, oh, this curve just goes on and on. But it does not increase infinitely, it gets flipped at this position. And as you increase your input voltage even more, it will stay here. It will not increase at all, it will also not decrease.
Yeah, I just want to clarify, when it reaches 0, that means it's hit the VCC potential, right?
Exactly, that's one way to, I mean, you're correct that if it reaches VCC, then it will definitely get flipped. But in real amplifiers, even before you see it is reaching VCC, it starts getting flipped. And so this occurs even before it actually reaches VCC. And there are reasons behind that which we'll learn later in that course. Okay. So if someone tells you that amplifier's gain is 5, just take it with a pinch of salt that it will be 5 if the amplifier is in the linear region. If it goes to the nonlinear region, it will not be 5. And that would be the reason why you might see that in your lab assignments, the amplifier is not giving you the expected gain. Right? It can happen. And the reason behind that would be that the amplifier is not in the linear region anymore. All right. So that's what I have written in some of these slides, that if you are assuming the amplifiers to be linear, you can just keep on cascading them one after another, and the gain will keep on increasing as you connect one amplifier after another. All right. Now let's look at an example problem for voltage gain. This is based on what we learned in the last class. So I'll draw these circuits on the board. Maybe I'll use this one. All right, the problem that you're seeing on the Zoom screen right now is this, that you have a voltage here. Let's call it Vs for V source. Then you have a resistance here, R1. You have R2 over here. You have R3. And you have R4. The voltage across R4, so if you're looking at this voltage, this is your output voltage that you have defined in this circuit. And you're asked to find out what is the voltage gain. What is the voltage gain, which is the ratio of output voltage to the input voltage. And the voltage division and equivalent resistances that we learned in the last lecture to express the gain as a cascade of different factors. All right. So first of all, how do we analyze this circuit? Generally, a voltage division or a current division analysis, you start from the end. You start from the end and then work your way backwards toward the source. So eventually what you want to know is that what is the equivalent amount of resistance that is connected in this network, and you want to represent your output voltage to input voltage ratio as a function of all those resistances. So as you walk your way back from the output side to the input side, first thing that you encountered is these two resistances, R3 and R4. Now, are R3 and R4, are they in series or are they parallel to each other? They are in series, perfect. So what is the overall combination? R3 plus R4, right? That's what you're seeing in the screen. So the overall combination that you see here is R3 plus R4 because they are in series. So I can simplify this and draw a resistance which is R3 plus R4. So now you see that it is hard to define your output voltage because your output voltage is now hidden. Your output voltage was the voltage across R4. Now you do not have a resistance that is called R4. You just have R3 plus R4. So you have to keep that in mind that your output voltage is now hidden, and we'll go back to that later. So you have R3 plus R4. Now, if you look into the next slide, which is basically representing what you see here. So now you see two resistances. One resistance is R2, and the other resistance is R3 plus R4. Are they in series or in parallel? They are in parallel, perfect. So what you see from here, this is R1, and what you see from here is R2 in parallel with R3 plus R4. Okay, so let's just represent all of that with just one resistance. So we are kind of simplifying the circuit. So you have R2 in parallel with R3 plus R4. That's what you have at this point. Okay, now let's call this point's voltage as Vy, an intermediate voltage which is Vy. And that Vy is going to be a voltage division between R1 and this complex resistance of R2 in parallel with R3 plus R4. You already know the formula of voltage divisions. You know that the voltage that you are trying to find out, so which is the voltage across this complex resistance, will be directly proportional to the value of the complex resistance. So your complex resistance of R2 in parallel with R3 plus R4, that will be in your numerator, and your denominator will be R1 plus R2 in parallel with R3 plus R4. Okay, that is again just from the basic formulas of voltage division. All right, so that is your Vy, that is the voltage at this node. Now that we have gone far back towards the source side, so for example, this was the source node, this was the next node, and you found out what is the voltage at this next node right after the source. So this source node had a voltage of Vs. The next node is this one, which has a voltage of Vy. Now you will work your way toward the load side again, because you know the voltage at this point. It will be easy to find out the voltage at the next point, and so on. All right. So you had R2 in parallel with R3 plus R4, right? That's what you had at this point. So now if I expand this again, you have R2 in parallel with R3, which is here, and R4, which is here. All you want to do was to find out the voltage here, which is V naught or VO, V out. And you've already found out the voltage here. So if you have the voltage here, what would be the output voltage VO? That would be R4 divided by R4 plus R3 times Vy. And Vy was this ratio of resistances times Vs. Right? Vy was the voltage at this point, which was that ratio of resistances times the voltage at the input side, which was Vs. And this is your output voltage VO, R4 divided by R4 plus R3 times Vy. And you already know what is the value of Vy. So you can substitute that. You can find out the value of VO as a function of Vs and all those resistances. So effectively, you can find out what is the ratio of VO or V out over V source. That is your gain. Right? So that's going to be your method as you are trying to find out all the voltage divisions in the circuit. So that's what we are showing in this particular example. Any questions? All right. So the next thing that is that if you wanted to find out the output voltage as the voltage across this resistance R3, so let's call it output voltage 2. Let's say this is your output voltage 1. Say you want to find out this as VO1, and you also wanted to find out the output voltage 2, VO2, as the voltage developed across the R3 resistor. In that case, you would write VO2 as R3 divided by R3 plus R4 times Vy. Now again, you already know your value of Vy, so you can find it out as a function of Vs and all other resistances. But important thing to note here is your VO2 is directly proportional to R3 because VO2 is the voltage developed across R3. Okay, so depending on which voltage is your output voltage, you may want to choose your voltage divisions carefully. All right. Now, the next problem that you see on the screen is basically a current gain or a current division problem. So I can probably draw that on the other side of the board. All right. So instead of a voltage source, let's say you have a current source. And that current source is called IS, again standing for I source. Then you have a resistance R1 to ground. Let's say you have a resistance R2 over here. You have R3. And you have R4. And the current going in this direction over here is IO or the I out. So basically I out is the current that flows through the R4 resistance. You are asked to find out the current gain, and again gain will always be defined as an output quantity divided by an input quantity. So let me write that down here. That gain will be defined as an output quantity divided by an input quantity. Now, as you have already looked into these two problems, the problem over here and the problem shown over here, your output could be a current or a voltage, right? Your input could be a current or a voltage. So you'll have 4 different combinations of gain depending on whether your output and inputs are voltage quantities or current quantities. So if your output is a voltage, let me first define those 4 scenarios for you. That if your output is a voltage, so let's say your output is voltage, input is voltage. So V out over V in. So that will be called a voltage amplifier. If you have a input or let's output current divided by input current, that is going to be called a current amplifier. This ratio I out over I in, that's going to be called a current amplification gain. if you have an output voltage, so V out, but an input current. So it's possible to have output voltage and an input current. For example, in this particular scenario, if I ask you that, okay, you consider this voltage as your output voltage. So you have output voltage, but if you have an input current. The ratio of the output voltage to input current, that's also a type of gain. So don't assume that the gain is always unitless. The gain can be a voltage gain. In that case, it is unitless. A gain can be a current gain. In that case, it is unitless. But the gain could be V out over I in. The output quantity could be voltage. The input quantity could be current. And in that case, you know that the voltage over current is a resistance or an impedance, right? So if your output is a voltage quantity, if your input is a current quantity, then that gain is going to be called a trans impedance gain. So let me write that down. So this is voltage gain. So I'm not writing it down. You already know that this will be called a voltage gain. This will be called a current gain. This will be called a trans impedance gain. Why trans impedance? Because you're transferring a quantity out input current quantity to output voltage quantity. So you're transferring one quantity to another. And that quantity, the gain quantity is an impedance or a resistance. Right? And that's why you call it a trans impedance or a trans resistance gain. If your output is voltage and your input is current. Yes.
What happens if your output is current?
Great question. So maybe you can answer it yourself that if your output is a current and your input is a voltage, that is still also possible. So for example, let's go back to the first problem. And let's say I define that the current going to R4 is my output quantity. Let's say I define my output quantity is this. So you have a current at the output, you have a voltage at the input. The gain is output current divided by the voltage input, which is this. That is transferring your input voltage to an output current. The ratio of current to voltage, what is that called? Conductance, right? 1 upon resistance is called conductance. So this gain is going to be called a transconductance gain. So remember, depending on whether your output and input quantities are voltages or currents, you may have a voltage gain, which is voltage over voltage. You may have a current gain, which is current over current. You may have a trans resistance or a trans impedance gain, which is voltage over current. And you may have a transconductance gain, which is current over voltage. So this is transconductance gain. And there would be a quantity called transconductance, which we'll be using heavily in this entire course when you get to MOSFETs. So transconductance will mean that you apply an input voltage and you get an output at the current. That's the transfer function. Again, what transconductance means? That the transfer function is a conductance. What transimpedance means is the transfer function is an impedance. And what does transfer function mean? The ratio of your output quantity to input quantity, that is the quantity that you're transferring from your input to output, right? That's the transfer function. And that transfer function could be unitless, it could be a conductance, it could be a resistance, depending on whether you have voltages or currents. Okay. All right. So now let's solve this problem using current division because we can. You can also solve it using voltage division, right? So whatever is easier for you. If you think that thinking in terms of voltage is easier for you, please go ahead and do that. But because this is a class, we are going to look at two different problems where once we solve it with voltage division, and this problem we are going to solve with current division. But you are free to do whatever way you want to do. Eventually, your goal will be to find out what is your output current to input current ratio. All right. So again, let's do the same thing. Start from the output, walk your way backwards toward the input. What is the first thing that you see? You see R4, and then in parallel, you see R3. So if I ask you to find out what is the resistance seen at this point, it is going to be R3 in parallel with R4, right? So looking on this side, you have R3 in parallel with R4. That is the resistance you see looking toward the right from the right-hand terminal of your R2 rail. So let's just replace this with one single resistance, which is R3 in parallel with R4. Again, you see that the current through R4 was our output quantity. The output quantity is now lost. It is hidden. It is hidden inside this R3 parallel R4 term. So you don't have direct access to your output quantity, but we'll again go back to it once we walk our way backward to the input side, and then we'll walk our way forward to the output side. Okay, so you have R3 in parallel with R4 over here. Then you see you have R2, which is in series with this complex resistance term. So if you want to find out the resistance over here, that is going to be R2 in series with R3 in parallel with R4. Right? So you have R2 plus R3 in parallel with R4. Okay. Now you see you have a very simplified network. You have a current source over here. The current goes out, gets divided into two resistances. And you already know how to find out how the current gets divided into two different resistances, right? So what would be the resistance that flows through this path? Let's call it again IY, some intermediate current value IY that flows through this complex resistance. And you know that the resistance flowing through one branch will be directly proportional to the value of the resistance in the other branch, not on the same branch, right? Because current is opposed by resistances. So that's why the other branch's resistance is something that will be there in the numerator. So this current that is flowing through this branch, which is IY, so this current is going to be IY, which is equal to R1 divided by R1 in parallel with R2 plus R3 in parallel with R4 times IS. So that's going to be your so you have R2 in plus R3 in parallel with R4, and then you have R1. Oh, sorry. Yeah, I think that's fine. Yeah. So that's going to be the value of your current IY, which is flowing through this complex resistance. Yes. Okay, so let's go back once again. So let's say you have a current IS, and you have one resistance R1, and you have a resistance R2. So let's simplify this once more. So you have R1, you have R2. What you're interested in is that what is the current flowing through R2? And that current, let's call it IY, is going to be R1 divided by R1 plus R2 times IS, right? This is something we proved in the previous lecture, last lecture. So this is the same thing I'm doing here. Now, instead of R2, or let's call it Rx, you have this quantity, right? This quantity is R2 plus R3 in parallel with R4. So that's what I'm replacing here. So you have R1 divided by R1 plus Rx, and this is the Rx quantity. So it's the same thing as we learned in the last lecture. It's just that this resistance is now a complex looking resistance. Okay, so that's how you find out what is the value of IY, that is the current going in this direction after your resistance R1. All right, now if we go back to the full circuit, that what did you have here? You had R2 plus R3 in parallel with R4. So you basically had R2, and then you had R3, and then you had in parallel R4. You already found out what is the current coming in here, because the original input current IS was getting divided into two parts, one going through R1 and one flowing on the right hand side through that complex network of resistances. You already found out what is that current IY, which is flowing through this complex network of resistances. Now that current flowing in will be divided into two parts again. One will go through R3 and the other one will go through R4. And the one that goes to R4 is the output quantity that you want. That will be your I out or IO. So again, it's just again a simple, very simple current division. Your IO or I out is R3 divided by R3 plus R4 times IY. So whatever current that was coming in, that gets divided into two parts. Again, if you want to find out the current flowing through the R4 resistance, that will be directly proportional to the value of R3, the other resistance, because current is opposed by resistances. So if a resistance is small, you'll have more current. If a resistance is large, you'll have less current. And that's why you have this other current over here, something that we proved in the last lecture. So that is going to be your IO as a function of IY. You have already found out what is your IY as a function of IS, and these resistances R1, R2, and R3, and R4. So you replace that as your IY, and you get the full equation of IO as a function of IS. For your current gain, you would want to find out what is the ratio of IO divided by IS. That's your current gain. And that's something you can find out from these two equations. Okay, so that's basically the problem that we looked at over here. Okay, now the next slide that you're seeing right now on the Zoom screen is basically something that we already talked in the beginning of the lecture. That always remember, your amplifier performs AC amplification and not DC amplification. What you saw here was a few very simple examples of voltage division and current division. But we are calling the output quantity divided by the input quantity a gain. Okay? We did not have any active amplifier here. You did not have an op-amp in this circuit. Still we talked about the concept of gain, because the concept of gain is universal. Gain just means output divided by input. Whatever quantity you have your output, divided by the whatever quantity you have at your input. So that's just a universal definition of gain. If you had an amplifier somewhere in between, let's say I include an amplifier over here with a gain of A or a gain of 5, then things will be different. Now, what you are seeing right now in the screen is when you talk about amplifiers, we'll always be talking about AC amplification and not DC amplification. Here, AC or DC does not matter. When you have these passive resistors, capacitors, inductors, what you have at the input quantity, this VS, this voltage source, this could be a AC voltage source, this could also be a DC voltage source. It doesn't matter. Because resistances react to AC and DC quantities in the same way. If you have a DC voltage of 5 volts, that will get divided into the same way between these two resistors as compared to the scenario when you, let's say you have an AC voltage of 500 millivolts. So whether you have an AC voltage source or a DC voltage source, that does not matter to the resistor. Resistors are passive. On the other hand, your amplifier is an active component. And for your amplifier, it matters whether you have an AC voltage source, AC current source, or a DC voltage source or DC current source. So that is again one other difference between active components and passive components. Okay. All right, so we maybe have 2 or 3 more minutes. We'll not look at a different problem today, but I'll be defining a few things about amplifiers in the next 2 minutes. So you already know about op-amps from your 3111 class, right? And you know that, again, op-amp is an operational amplifier. And the symbols for an op-amp may look like this, what you have already known. So you have an input between these two terminals, let's say the positive terminal and the negative terminal, you have a gain of A and you have an output quantity over here. That's what you have learned in the previous classes, right? This is how an op-amp looks like. Now, along with that, you have learned about some properties of an op-amp. What are the properties of an op-amp? One property is that the op-amp has infinite input impedance. So if you look into the input side and you find out what is the resistance or what is the input that you're seeing, that would be infinitely large. Because you have learned that there is no current that goes into the op-amp. In this course, we'll learn why there is no current that goes into the op-amp. We'll learn that, but not today. We're going to learn why there is no current that can go into the op-amp. We'll learn that later. But right now, let's remember that the op-amp ideally have an infinite input impedance. The op-amp also has a zero output impedance. So your output impedance is equal to 0 if you look from the output side. What does that mean? That at the output side, you can kind of modulate that this impedance is kind of connected to a ground. And from the input side, you have Z in equal to infinity. And your gain ideally is infinitely large. So those are the properties of an ideal op-amp. Also, along with that, there are some other properties, for example, infinite bandwidth. Because when you talk about an ideal op-amp, you assume that the op-amp can have gain at any frequency. At 1 Hertz frequency, at 1 kilohertz frequency, at 1 gigahertz, 1 terahertz, it does not matter. That's what you assume, that it can provide gain at any frequency, which will not be true for real op-amps. Real op-amps will have a finite bandwidth as well, that it will only amplify certain signals, certain frequencies, and not amplify other frequencies. So those will be the difference between ideal and real op-amps. We'll stop here, and the next lecture we'll be discussing more related to real op-amps.
I just want to say thank you so much. Like, this is the first time I feel like I understood your part. You know, we're doing like practice. I need to
It's like anything to
brush up on like
The voltage correction.
Yeah.
Yeah. So I have uploaded a few example problems on Canvas. Let me
Yeah, because when I was with whatever circuit one, like I had rainbows. It was reverse style classroom. I had to teach myself, but I never really.
Okay.
But
No, I think I'll make sure that you have enough practice problems so that it's easier to learn.
yeah, 'cause I'll start with.
Yeah, let me stop the recording first.